Usually when we talk about a magical experience, like, say, walking into a Michelin star restaurant and having this unbelievable, perfectly plated meal just set down right in front of you, there's this expectation of pure alchemy, right?
Right, yeah. You just want the experience.
Exactly. You don't want to think about the walk-in freezer. You really don't want to think about the global supply chain that got the truffles there, or the refrigeration logistics, or, the kitchen staff crying while they chop 50 pounds of onions. You just want the magic.
Absolutely.
But if you step into the world of enterprise machine learning, and specifically, the realities of engineering these systems in Google Cloud, you have to care very, very deeply about those onions. Because in this world, if your data plumbing fails, your billion-dollar predictive algorithm is, well, it's entirely useless. So today, we're ripping the doors off the Google Cloud ecosystem for a really intense deep dive to see how these predictive engines are actually built.
It really is an industrial kitchen of data plumbing, like you said.
Yeah.
I mean, the illusion of artificial intelligence is just that. It's an illusion.
Yeah. The finished product seems flawless, but underneath, it is the absolute definition of a highly orchestrated, surprisingly grounded logistical operation. When you're engineering for machine learning, you are building a factory.
And we're looking at some specialized architecture materials today that detail this exact journey, especially if you're out there preparing for the professional machine learning engineer track on Google Cloud. This is exactly what you need to know. And the foundation of all of this, the core premise that dictates whether your system succeeds or fails, is data quality. We always talk about the ML workflow having 3 stages, right?
Right. Data preparation, model training, and model serving.
Sourcing the ingredients, tweaking the recipe, and then serving the customer. But the absolute dependency here is that you just cannot bake a world-class cake with spoiled milk.
You really can't. If the milk is sour, the cake is garbage. And, we hear garbage in, garbage out constantly in tech, but at an enterprise scale, it's a bit more insidious. It's more like a subtle bias in, catastrophic business failure out.
Oh, wow. Yeah, that's a good way to put it. Because data is the only thing the model uses to derive its predictive insights. If your preparation phase feeds the algorithm poorly formatted or inconsistent or just anomalous data, you are mathematically guaranteeing flawed predictive insights when you finally serve that model to real customers.
Right.
You don't just get a slightly worse model, you get a system that confidently makes the absolute wrong decisions at scale.
Which is terrifying for a business. So to understand how those decisions are made and how a machine actually, attempts to learn from the ingredients we give it, we have to get into the mathematical bedrock of model training. Because when an ML engineer looks at training, they aren't looking at a sentient brain. They're looking at an optimization problem.
Exactly.
They're looking at a landscape. So let's unpack this. Let's talk about the descent into the valley.
Right. Gradient descent. This is really the engine of all modern neural network training. To kind of wrap our heads around this without a chart in front of us, imagine a highly complex, multi-dimensional mountain range. Your model's error, so how wrong its predictions are, is represented by elevation. The higher up you are on the mountain, the worse the model is performing. The machine's entire purpose in life is to find the lowest possible point in that landscape.
The bottom of the deepest valley.
Exactly, which
Yes.
represents the minimum possible error.
But the catch is the model is blindfolded, right? I mean, it drops into this landscape at a completely random starting elevation, and it can only feel the slope of the ground immediately beneath its feet. It has to calculate the derivative, like the slope of the curve at that exact coordinate, to figure out which way is down.
Yeah, and this is where the computational heavy lifting really happens. Because calculating that slope isn't just looking left or right. In a modern neural network, you might be dealing with millions or even billions of dimensions.
Right. It's not just a 3D physical landscape like we're used to.
No, not at all.
Yeah.
So the model computes what's called a gradient vector, which actually points in the direction of the steepest descent. So to go down, it moves in the exact opposite direction of that vector.
Okay, so we know the direction. The model says, all right, downhill is this way. But then we hit this crucial parameter, which is the step size. Like, how far do you walk in that direction before you stop, recalculate the slope, and take another step? And this is what we call the learning rate.
Yeah, and the learning rate is basically the ultimate Goldilocks problem in optimization.
How so?
Well, if your step size is too small, you're taking like millimeter steps down a mountain. You will eventually reach the bottom, which we call convergence, but the computational cost is astronomical.
Because it's doing that massive derivative math for every tiny millimeter.
Exactly.
Yeah.
You are recalculating gradients on massive data sets for every single tiny step. It takes forever, and you are just burning through really expensive GPU compute.
Right. So, I mean, the natural business instinct there is going to be take massive leaps, get to the bottom of the valley immediately, save money.
But if you take a step that is too large, you launch yourself over the valley entirely.
Oh, right.
You start on the left slope, you take this massive jump, and you land way up high on the right slope.
Then you recalculate. The gradient says downhill is back the other way. You take another massive leap, and you just end up bouncing wildly back and forth across the ravine.
Yeah, you might even diverge, like climbing higher and higher up the mountain, which completely destroys the model's performance.
So wait, if I'm hiking down a mountain blindfolded, and I know small steps take forever and large steps overshoot, I'm going to take huge strides when the slope is incredibly steep, and I know I have a long way to go, is right? But as the ground starts to level out, as I feel myself getting closer to the valley floor, I'm going to naturally shorten my stride so I don't overshoot. So why are we locking ourselves into a static step size before training even starts?
That's a great question, and it's exactly why static learning rates are largely a thing of the past in advanced engineering. Modern architectures use what we call adaptive learning rate optimizers.
Like Atom or RMSE.
Exactly, yeah. They do exactly what you just described. They dynamically adjust the step size via the historical gradients. If the slope has been consistently steep in one direction, they kind of build up momentum and take larger steps.
Makes sense.
But then when the gradients start shifting wildly, which indicates you're near a complex valley floor, they decay the learning rate and start taking smaller, much more careful steps.
Okay, but even with adaptive optimizers, the human engineer isn't totally off the hook, right? You still have to configure the baseline parameters for that adaptability. The human provides the framework, the machine just executes the iteration. And I feel like that dynamic brings us to the anatomy of the artificial brain itself, the neural network.
Definitely. And what's fascinating here is when we talk about the structure of a neural network, we usually describe, the input layer, the hidden layers, and the output layer. But the critical distinction an ML engineer really has to internalize is the strict division of labor between what the machine learns and what the human dictates.
We're talking about parameters versus hyperparameters.
Yes.
Because we hear those terms thrown around interchangeably by people outside the field constantly, but they are fundamentally different things.
Very different. Parameters are the weights and biases inside the network. These are the actual coordinates on that mountain we were just talking about.
And crucially, the machine decides the parameters during the training process.
Right. An engineer doesn't sit down and hard code the weight of neuron number 4000. That would be impossible. The gradient descent algorithm, using backpropagation, mathematically tweaks those weights slightly with every single epoch, every single pass through the data to minimize the error. So the parameters are what the model have actually learned about the data.
But then we have the hyperparameters, and this is where it's so funny because we call it artificial intelligence, but the hyperparameter side looks a lot more like human intuition. Hyperparameters are the architectural blueprints, right? They dictate how the model learns.
Exactly. How many hidden layers are in this network? Are there 10 layers or 100? How many neurons are in each layer? What activation function are we using to introduce nonlinearity? Are we using a ReLU function or like a sigmoid function? What is that baseline learning rate? How many total epochs are we going to run before we cut the compute?
Every single one of those decisions is made by a human being before the training even begins. I mean, the machine has absolutely no say in its own architecture. If an engineer gives a neural network too few layers to capture the complexity of the data, it doesn't matter how many times you run gradient descent. The machine is mathematically handicapped.
Yeah, it's confined by the physics of the universe the human built for it. It really is entirely human-directed iteration. The machine just provides raw, relentless computational stamina to calculate derivatives millions of times.
While the human provides the structural intuition to ensure those calculations are actually meaningful. So what does this all mean? The human builds the kitchen, sets the rules, and the machine tirelessly turns the knobs on the oven trying to find the perfect temperature.
That's a great analogy.
But then, how do we evaluate the final meal? Because measuring performance isn't just a matter of saying, hey, the model is 90% accurate. In the real world, accuracy is often a super dangerous vanity metric.
Oh, absolutely. Accuracy can be incredibly misleading, especially if you're dealing with imbalanced data sets.
Right.
Like, if you are building a system to detect credit card fraud, and only 1 in 10,000 transactions is actually fraudulent, Your model could literally just output not fraud every single time without doing any actual analysis, and it would technically be 99.99% accurate.
But it would be a completely useless model.
Totally useless. This is why we have to evaluate performance based on the specific business problem.
Okay, so let's start with predicting continuous numbers, like a forecasting model. It's trying to predict next quarter's revenue. The core metric here is often RMSE root mean square error.
Yeah, so RMSE takes the difference between what your model predicted and what actually happened, squares that difference, averages all of them across the data set, and then takes the square root.
But the mathematical quirk here, and this is what's important for the listener to know, is the squaring part. Because you square the error before averaging it, RMSE violently penalizes large errors.
Yes, it does.
Like if your model predicts a house will sell for $300,000 and it sells for $310,000, that $10,000 error squared is a certain penalty. But if it predicts $300,000 and it actually sells for $3 million, that massive error is squared and it completely dominates the final metric.
Which means you use RMSE when your business just cannot tolerate massive misses. If a slight miscalculation in inventory costs you a little bit of money, but a massive miscalculation bankrupts the company, you use RMSE as your loss function.
Because it mathematically forces the model to avoid those huge outliers.
Exactly. Now, if you wanted to treat all errors equally, regardless of size, you'd use MAE mean absolute error, which just takes the absolute value and doesn't square the differences.
Okay, but what about classification? Not predicting a number, but predicting a category. Like, is this email spam? Is this a fraudulent transaction? This is where we get into the tension between precision and recall. And looking at the source materials, this tension is essentially a business negotiation that's masquerading as math.
It is entirely a business decision.
Mm-hmm.
Let's look at the mechanics of it. You have a confusion matrix. You have true positives. The model caught the fraud. You have true negatives. The model correctly ignored a normal transaction. Those are your successes.
Right.
The tension lies in the errors,
Fair.
the false positives and false negatives.
So a false positive, which is a type 1 error, is the model sounding the alarm when nothing is actually wrong. It flags a legitimate purchase as fraud and locks the customer's credit card.
Right.
And a false negative, a type 2 error, is the model falling asleep at the wheel. A truly fraudulent transaction slips through completely unnoticed.
And the brutal reality is you cannot minimize both to zero in the real world.
Yeah.
You have to choose where you want your model to lean. This is that balance of recall versus precision.
So how do you explain the difference to a business stakeholder?
I like to use the fishing analogy from the materials. Recall asks, out of all the actual positive cases out there, how many did we predict correctly? So out of all the actual fraud in the world, what percentage did our system successfully catch?
Okay.
If you want high recall, you cast a massive aggressive net. You catch, say, 80 fish out of a lake of 100. That's 80% recall. You got almost all the fraud. But because your net is so aggressive, you scoop up 80 rocks, too. Your false positives skyrocket.
Right, which totally destroys your precision, because precision asks, every time our system sounds the alarm, every time we pull up the net, how often is it actually right?
Exactly. If you want high precision, you use a tiny, highly targeted net, or a spear.
Well,
You only sound the alarm when you are 99.9% mathematically certain it's fraud.
so you only catch 20 fish, but 0 rocks.
Exactly. 100% precision. Your false positives drop to almost zero. Legitimate customers are never inconvenienced. But because you are being so cautious, your false negatives skyrocket. A ton of actual fraud slips past you.
Here's where it gets really interesting when you apply it to the real world. Think about the business implications of a Gmail spam filter. If Google prioritizes high recall, catching every single piece of spam in existence, the side effect is that legitimate emails, like an email from your boss or a boarding pass, get classified as false positives and thrown into the spam folder.
Right. And for an email provider, a false positive is catastrophic.
Exactly. Users will tolerate a little bit of spam in their inbox, which is a false negative, but they will abandon a service forever if they miss a critical flight update. So spam filters are tuned heavily toward precision.
But if we flip the scenario to, say, a medical diagnostic model screening for cancer,
It's exactly the opposite.
completely the opposite. You have to optimize for recall because a false positive means you tell a healthy patient they might have cancer, you run a second test, realize the mistake, and everyone is relieved. It's stressful, sure, but it's not fatal.
Right. But a false negative means you send a sick patient home telling them they are totally fine and the disease goes untreated.
Exactly. In medicine, a false negative is catastrophic. So you cast a wide net. You accept lower precision to guarantee high recall.
But when you are training the model in the lab, you often don't know exactly what threshold the business leaders are going to want to set, right? Like, you need a way to measure the overall capability of the model across every possible threshold, from ultra cautious to hyper aggressive.
Yeah, and that is what the AUC ROC curve provides. The area under the receiver operating characteristic curve.
That's a mouthful.
It really is. But what it does is it plots the true positive rate against the false positive rate across all classification thresholds. It essentially measures the probability that the model will score a randomly chosen positive example higher than a randomly chosen negative example.
So an AUC of 1.0 means the model perfectly separates the two classes.
Right, and an AUC of 0.5 means the model is absolutely no better than a random coin flip. It's a great aggregate measure because it gives you a single metric to compare two entirely different neural network architectures before you deploy them or even decide on your threshold.
Okay, but in the pursuit of building a model that drives that AUC close to 1.0 or drives that RMSE down to 0, there is a massive architectural trap. A trap that looks like wild success on paper, but results in total failure in production. We're talking about the memorization trap. Overfitting versus complexity.
Yes, the fundamental tension in model training is minimizing error versus maintaining simplicity. If you give a complex neural network enough layers, enough neurons, and enough time to iterate over a data set, it will eventually achieve zero error on that data.
It'll just learn it perfectly.
Exactly. It will perfectly predict every single historical example you give it.
And I mean, to an untrained eye, zero error sounds like the ultimate goal, right? You fed it historical stock prices, and it perfectly predicted the exact movement of every stock over the last 5 years.
But real-world data isn't clean. It contains signal, the underlying mathematical truths and trends we actually want the model to learn. And it contains noise, random fluctuations, sensor glitches, anomalies.
Just weird stuff that happens once.
Right, so when a model is overly complex, it doesn't just learn the signal, it perfectly memorizes the noise. It treats random historical fluctuations as if they are fundamental laws of physics. It contorts its mathematical boundaries to perfectly encompass every single outlier in the training set.
So it's like a student who just memorizes the practice test but doesn't actually learn the subject.
That's a perfect analogy. Because what happens when you deploy that model? Tomorrow's stock market data arrives. It has the same general signal, but entirely new random noise.
And because your model is a frantic, hyper-customized zigzag designed only to fit yesterday's specific noise, it just fails catastrophically on the new data. Overfitting is memorization, not learning.
Exactly. And this is why the golden rule of machine learning is that you never, ever evaluate a final model on the data you used to train. You have to split your data set. You use the training set to adjust the weights. You use the validation set to tune your hyperparameters during development. And you lock a test set away in a vault.
The model never sees it.
Never. Only when the architecture is totally finalized do you run it against that test set. If it performs perfectly on the training data, but terribly on the test data, you know it overfit.
Okay, but if we realize the model is overfitting, how do we physically stop it? Like, what are the tools? The sources talk about regularization.
Yeah, regularization is how we actively penalize the model for being too complex. We basically alter the cost function we discussed earlier. Instead of just calculating error, we add a complexity penalty. The model is now trying to minimize error plus complexity.
Okay. And I see L1 and L2 regularization brought up constantly.
Right. Those are the standard mathematical approaches here. They place penalties on the size of the weights inside the neural network. L2 regularization, which is also known as ridge, adds a penalty equal to the square of the magnitude of the weights.
And because it squares them, similar to RMSE, it punishes excessively large weights really heavily, right?
Exactly. It forces the model to distribute its reliance across all features smoothly, rather than hyperfixating on one single variable.
Got it. And L1 regularization, or lasso, adds a penalty equal to the absolute value of the weights. But the mathematical quirk of L1, which I always find fascinating, is that it actively drives the weights of less important features down to exactly 0.
Yes. It acts as an automatic feature selector. If you feed the model 1,000 variables, L1 regularization will aggressively shut off the hundreds of variables that are just contributing noise, leaving you with a much simpler, more robust model.
That's so smart. And there are other ways too, right? Like early stopping.
Oh, definitely. Early stopping is incredibly common. It literally just monitors the validation error during training, and the moment the error stops improving and starts getting worse, which means it's starting to memorize the noise, you just cut the compute power and freeze the model. You prevent it from having the time to overfit.
Simple but effective. And then there's data augmentation. Like if you are training an image recognition model to identify cars, you don't just feed it the basic photos. You programmatically rotate the images, crop them, change the lighting, maybe add some artificial static.
Right. You force the model to learn the fundamental geometry of a car, rather than memorizing the specific pixel arrangement of your limited data set.
Okay, so we've established the mathematics of learning. We know how to navigate the valley of gradient descent, how to measure the real-world business impact of our predictions with AUC and recall, and how to stop the model from memorizing the textbook. But at an enterprise scale, none of this happens in a vacuum. You don't execute these workloads on a laptop.
No, definitely not.
You need infrastructure capable of handling petabytes of information with near zero latency. Which brings us to the Google Cloud Storage ecosystem. The pantry, so to speak. And honestly, navigating this architecture is where ML engineers really separate themselves from data scientists.
That's a great point. A data scientist focuses on the math. An ML engineer focuses on the pipeline. And the pipeline starts with where the data lives. Now, Google Cloud provides an ecosystem that can look like an intimidating alphabet soup of databases to a newcomer. Cloud storage, Spanner, Bigtable, Firestore, BigQuery. It is. But they actually represent a highly logical decision tree based on the fundamental nature of your data.
Okay, let's walk that decision tree for the listener. The primary fork in the road is unstructured versus structured data. Unstructured data is, well, the messy stuff. Audio files, raw video, millions of disorganized PDF documents, high-resolution images for a computer vision model. They just don't fit into rows and columns.
Right, and for unstructured data, the universal landing zone in GCP is Google Cloud Storage. It's an object storage system. You aren't defining strict tables, you're just dropping files into a massively scalable bucket. But the architectural decision here comes down to access frequency and cost. GCS forces you to choose a storage tier.
Right, like standard storage is for hot data. You are actively streaming these images into your GPU cluster for model training right now. The storage cost is a bit higher, but the retrieval latency is practically zero.
Exactly. But if we are legally required to keep raw sensor logs for 7 years, and we only ever look at them if there is a catastrophic failure, we absolutely do not put that in standard.
Right, you move down the tiers. Nearline is for data accessed maybe once a month. Cold line for once a quarter, and archive is for data you access less than once a year.
And the storage cost for archive is fractions of a penny. But, and this is a big but, if you suddenly need to pull a petabyte of data out of archive to retrain a model, you will pay a massive retrieval penalty, and it will take hours. So the economics force you to be really architectural about your data lifecycle.
Okay, that's unstructured. But the vast majority of enterprise machine learning runs on structured data, data that fits cleanly into schemas, rows, and key value pairs. And here, looking at the sources, the decision tree splits based on workload type, transactional versus analytical. This distinction is like the bedrock of database architecture, OLTP versus OLO.
Let's define the mechanics of that for a second. A transactional workload, OLTP, online transaction processing, is about the live day-to-day operations of an application. It's a banking app recording a $4 coffee purchase. It is characterized by millions of tiny, simultaneous, rapid-fire read and write operations. The database has to ensure strict consistency. If two people try to buy the exact same concert ticket, the exact same millisecond, the database must flawlessly lock the row, grant the ticket to one, and decline the other without corrupting the entire table.
Wow, yeah. Contrast that with an analytical workload, OLOP, online analytical processing. This is where you are looking backward to find macro trends. You aren't processing a single coffee purchase. Your data science team writes a query asking, hey, calculate the average profit margin of all coffee sales globally over the last 5 years, grouped by store location and cross-referenced with local weather patterns.
Right. It's a massive sweeping query that has to scan petabytes of historical data. Transactional databases process rows one by one instantly. Analytical databases scan columns by the millions, methodically. You simply cannot mix these workloads efficiently.
Okay, so let's look at the tools for transactional workloads first. Within transactional, we have SQL, which are relational databases with rigid schemas, and NoSQL, which are flexible document-based databases. If an enterprise has a transactional SQL workload, the standard choice is Cloud SQL, right?
Yes. It runs standard MySQL or PostgreSQL. It handles the back end of standard applications perfectly, but there's a ceiling to Cloud SQL.
Which is global scale.
Exactly. Cloud SQL is fantastic for local or regional applications. But relational databases fundamentally struggle with global distribution. If you have a database node in Tokyo and a node in New York, and you need synchronous transactional consistency across them, the sheer physics of light traveling through fiber optic cables introduces latency.
Right.
If you are a massive global enterprise, say a massive supply chain logistics platform, and you need absolute relational consistency globally, Cloud SQL will hit a wall. That is where you transition to Cloud Spanner.
And Spanner is just one of the most fascinating engineering feats in cloud computing. I mean, how does it actually solve that global consistency problem?
It solves it by bending the CIP theorem using atomic clocks.
Wait, actual atomic clock?
Literally, yes.
Yeah.
So the CIP theorem states a distributed system can only provide 2 of 3 guarantees: consistency, availability, and partition tolerance. Standard relational databases usually sacrifice partition tolerance to ensure consistency, but Spanner uses a technology called TrueTime. Google actually installed GPS receivers and atomic clocks in every single one of their data centers globally.
That is wild.
It is. TrueTime provides a highly precise, globally synchronized absolute time. Because every server agrees on the exact time down to the microsecond, Spanner can assign absolute, indisputable timestamps to every single transaction globally. This allows it to order transactions perfectly, providing synchronous relational consistency across continents without the massive latency bottlenecks that traditional databases face.
It is literally solving software problems with hardware physics. I love that.
Okay, but what if our transactional workload doesn't need a rigid relational schema?
Well,
What if we have a transactional NoSQL workload, like a mobile gaming backend, where player inventory data structures change with every single game update?
then you move to Firestore. It's a flexible, document-based NoSQL database that scales automatically. It doesn't force you into rigid tables, making it perfect for rapid application development.
Got it. Now let's jump over to the analytical side, the massive sweeping queries. Again, we have SQL versus NoSQL. For analytical SQL, the absolute titan of the Google Cloud ecosystem is BigQuery. And for a machine learning engineer, BigQuery is often the center of the universe.
BigQuery is incredible. It's a serverless enterprise data warehouse. The reason it can crunch petabytes of data in seconds is its underlying architecture. Traditional databases store data in rows. BigQuery uses a columnar storage format.
So if you run a query asking for the average price of a product, BigQuery doesn't have to load the entire row containing the product name, the description, and the weight. Exactly. It solely scans the price column across billions of records, and you combine that columnar storage with its Dremel execution engine, which automatically distributes a single SQL query across thousands of hidden worker nodes instantly under the hood. And you have an engine perfectly designed to prepare massive tabular data sets for machine learning.
Okay, and finally, the counterpart to BigQuery, analytical NoSQL. And looking at the materials, the architecture points to Cloud Bigtable.
Yeah, Bigtable is uniquely designed for relentless throughput. It is a sparsely populated table that can scale to billions of rows and thousands of columns. But it doesn't use standard SQL. It is specifically designed to absorb massive streams of flat time series data with sub-millisecond latency.
So like if you are building an IoT predictive maintenance model and you have 10,000 factory sensors sending temperature readings every 10 milliseconds.
Cloud SQL would completely buckle under that write pressure. BigQuery is designed for reading massive data, not absorbing millions of tiny writes a second. Bigtable uses a wide column sparse architecture that simply absorbs those writes into memory and flushes them to disk with incredible efficiency.
So mapping this out for the listener, cloud storage is the massive warehouse for unstructured raw materials. Cloud SQL is your highly organized regional filing cabinet. Spanner is the globally synchronized filing system running on atomic clocks. Firestore is the flexible corkboard for rapid app development. Bigtable is the relentless ticker tape absorbing millions of data points a second. And BigQuery is the omniscient supercomputer crunching the historical archives.
That's a really great summary.
Thank you. But, understanding where your data lives is critical, obviously. But data in a database is just human information. Neural networks don't understand text. They don't understand categories. They don't understand dates. They only understand one thing: vectors of floating point numbers. Before we can train a model, we have to translate human reality into machine reality. Which brings us to arguably the most critical, labor-intensive phase of an ML engineer's job: feature engineering.
Yeah, feature engineering is really the art and math of transforming raw data into representations that expose the underlying patterns to the algorithm. Let's say we are predicting the price of a house. The raw data we pull from our database might include the lot size, the number of bedrooms, the neighborhood name, and a Boolean flag for whether it has a pool.
Okay.
If we feed that raw JSON object directly into a dense neural network layer, the math just crashes.
Hmm.
We have to map those raw features into numerical feature columns.
For numerical features like lot size, it seems pretty straightforward, right? Just pass the number of 5,000 to the model. But if you pass raw lot sizes in the thousands and number of bedrooms in the single digits, the neural network's gradient descent is going to struggle wildly. The massive numbers will cause massive gradients, making that learning rate we talked about totally unstable.
Exactly. Which is why numerical feature engineering requires scaling and normalization. We use techniques like min-max scaling to squish all the lot sizes down into a standardized range, typically between 0 and 1, or we use z-score normalization to center the data around a mean of 0.
So that mathematically harmonizes the inputs so the neural network treats them on a balanced scale.
Precisely.
But the real complexity arises with categorical data, the neighborhood name, a string of text like downtown or suburbs. We have to turn a word into a number. And the immediate naive instinct is to just assign integers, like downtown is 1, suburbs is 2, rural is 3.
And that naive approach destroys the model, because neural networks interpret numbers as having mathematical magnitude and ordinal relationships.
Right.
If downtown is 1 and rural is 3, the model mathematically assumes that rural is 3 times as large or 3 times as important as downtown. It assumes downtown plus suburbs equals rural. You have just introduced completely false mathematical logic into the data.
So we have to use Keras preprocessing layers to fundamentally change the geometry of the data. We use one-hot encoding.
Yeah. With one-hot encoding, we create a vocabulary of all possible categories. Let's say we only have 3 neighborhoods. We create an array with 3 slots. If the house is in downtown, the vector is 1, 0, 0. The downtown slot is hot 1, and the others are cold 0. If it's suburbs, the vector is 0, 1, 0.
By doing this, we move the categories into a multi-dimensional space where every category is exactly the same mathematical distance from every other category. There is no false hierarchy.
Exactly.
But, and this is a big but, that is mathematically elegant for 3 neighborhoods. What if our categorical feature is user ID? What if an e-commerce platform has 10 million unique users and we want the model to learn individual purchasing behavior? If you apply one-hot encoding to 10 million users, every single row of your dataset suddenly expands into a vector with 10 million slots containing a single 1 point and 9,999,999 zeros.
And that is what we call the vocabulary explosion problem. The resulting matrix is so incredibly sparse and massively wide that it will cause an out-of-memory error on any GPU cluster you try to train it on. The computational inefficiency of multiplying matrices with that many zeros is just staggering.
So when you have infinite, unpredictable, or massive categorical cardinalities, one-hot encoding fails. We have to use more advanced preprocessing layers. And the materials point to 2 specific solutions: the hashing trick and embeddings. Let's unpack the hashing trick first. How does tf.keras.layers hashing solve the memory explosion?
By enforcing a strict ceiling on the dimensionality. Instead of creating a slot for every single user, you define a fixed number of buckets, say 10,000 buckets. You take the raw user ID string and pass it through a deterministic cryptographic hashing algorithm.
Okay.
The algorithm digests the string and spits out an integer between 1 and 10,000. It places the user in that bucket, and then you one-hot encode the 10,000 buckets instead of the 10 million users.
But mathematically, if you compress 10 million users into 10,000 buckets, multiple users are going to hash to the exact same bucket. You are intentionally mixing distinct users together. You are creating hash collisions.
You absolutely are. User A and user B will look identical to the model. But machine learning architectures are incredibly robust. They rely on the aggregate signal of all the other features in the dataset to differentiate the rows. The hashing trick is a deliberate compromise. You introduce a small amount of noise, those collisions, to achieve massive computational feasibility and memory safety. You use them when the categories are essentially infinite, and you don't really care about the granular relationship between specific individual users.
But what if we do care about the relationships? Like, what if our categorical variable is a catalog of 50,000 products, and we want the model to understand that a winter coat is conceptually similar to a scarf, but fundamentally different from a lawnmower? Hashing destroys that nuance. One-hot encoding ignores it entirely. This is where we use an embedding layer, right?
Yeah, and embeddings are arguably one of the most powerful concepts in all of modern deep learning. An embedding layer takes a high cardinality categorical variable and maps it into a dense, low-dimensional continuous vector space.
So instead of a sparse 50,000 slot one-hot array full of zeros, an embedding layer translates the product into a dense vector of, say, 64 floating point numbers, like 0.45 minus 1.2, 0.88.
Exactly. And the brilliance of an embedding layer is that those 64 numbers aren't just random, and they aren't generated by a static algorithm. They are actual parameters in the neural network.
Wait, so they learn during training?
Exactly.
Yeah.
The embedding weights are trainable. When you initialize the network, the 64 numbers for winter coat and scarf are random. They are scattered randomly in a 64-dimensional space. But as the model trains, as gradient descent calculates the error on predicting purchases, it backpropagates the error all the way down to the embedding layer and adjusts those 64 numbers. Over millions of epochs, the model physically moves the vectors in the mathematical space. So by the end of training, the vector for winter coat and the vector for scarf will have mathematically migrated to be right next to each other, simply because they appear in similar purchasing contexts. And the vector for lawnmower will be pushed far away.
So the model literally learns the semantic meaning and relationship of the categories by organizing them in a spatial geometry. That is incredible. Okay, so summarizing. One hot encoding for small fixed vocabularies. Hashing to prevent memory explosions on infinite, unpredictable categories. And embeddings to learn deep, complex semantic relationships within a large, known vocabulary.
Exactly right.
We have the storage architecture, we have the feature engineering translation layer, we have the training mechanics. Now, let's step into the shoes of a cloud architect and look at how these pieces are orchestrated together to build enterprise pipelines. Let's look at some real-world architectural blueprints derived from the scenarios in the engineering materials.
Let's do it.
Scenario 1. We have hundreds of millions of rows of tabular data sitting in BigQuery. The data science team has requested a custom TensorFlow classification model. Before training, we need to apply min-max scaling to the numerical features, and we need to one-hot encode the categorical product IDs. And the business constraint is strict: minimize operational effort and compute cost. So how does an architect route this workload?
An architect solves this by aligning the computational requirements of the transformation with the native strengths of the infrastructure. So we have two tasks: scaling numbers and one-hot encoding text for a neural network. We could build an external Apache Beam pipeline using Dataflow to extract the data, process everything, and feed it to the model. But Dataflow requires provisioning massive compute clusters, managing workers, and moving hundreds of millions of rows across the network. It violates the constraint of minimizing cost and effort.
Right. We want to leverage data gravity. We want to process the data where it lives.
Precisely. BigQuery is a colossus at crunching numbers. Executing a min-max scaling operation across hundreds of millions of rows in BigQuery takes a simple SQL query and executes in seconds using Google's distributed compute. So we let BigQuery handle the numerical scaling natively.
Okay, but what about the one-hot encoding?
Well, we could write complex SQL to pivot the text strings into one-hot columns. But we are building a custom TensorFlow model. TensorFlow has Keras pre-processing layers, like the category encoding layer we just discussed, that are specifically optimized to execute on GPUs during the training loop.
So the hybrid architectural solution is to use BigQuery to cheaply preprocess the numerical data, pass that scaled data and the raw categorical text to Vertex AI for training, and allow the TensorFlow graph itself to handle the categorical encoding natively. We separate the workloads to where the compute is cheapest and most efficient.
Yes. That is the hallmark of mature cloud architecture. You don't use a hammer for a screw just because you know how to hold a hammer.
I like that. But let's look at a scenario where we do need the heavy machinery. Scenario 2. A massive enterprise is streaming structured data into cloud storage in Avro format. The pipeline has to satisfy 3 completely different engineering teams simultaneously. Team 1 needs to perform massive historical analytics. Team 2 needs to engineer complex features. Team 3 needs to host those engineered features for a live, low-latency online prediction application.
This is a classic Lambda architecture problem. You need batch processing for history and stream processing for live serving.
Right.
Let's route the data. First, the analytics team. BigQuery natively integrates with cloud storage. We can set up a BigQuery external table to instantly ingest and query the Avro files, satisfying the analytics requirement with zero complex pipeline logic.
That's easy.
But for teams 2 and 3, we need to build complex features and serve them to a live app in milliseconds. BigQuery cannot serve single-row predictions to a live app. Its latency is measured in seconds, not milliseconds.
Right. This is where we bring in Dataflow and Vertex AI.
Exactly. We provision an Apache Beam pipeline running on Cloud Dataflow. Beam is a unified programming model that handles both batch and streaming data identically. The Dataflow pipeline reads the Avro data, executes the complex feature engineering math, and then writes the final, polished feature vectors directly into the Vertex AI feature store.
And the Vertex AI feature store is basically a centralized repository specifically engineered to serve those pre-computed features at ultra-low latency for online prediction models, right?
You got it.
But, building these pipelines introduces one of the most insidious, silent killers of machine learning systems in production. The system works perfectly in the lab, you deploy it, and its accuracy just totally tanks in the real world. I'm talking about training serving skew.
Oh, training serving skew is a nightmare to debug because it isn't a runtime error. The code executes perfectly. The math just slowly diverges from reality.
Yeah, and it happens when the pre-processing logic applied to the historical data during model training is subtly different from the pre-processing logic applied to the live data during serving.
It's exactly. Let's say a data scientist writes a Python script using pandas in a Jupyter notebook to clean the historical data, handle null values, and scale the inputs.
Yeah.
They train a beautiful model.
Beautiful model, great AUC.
Right. But the live application is a microservice written in Java. The software engineering team has to recreate the data scientist's Python logic in Java to pre-process the live user data before feeding it to the model.
And that translation is never perfect. A slight difference in how Python and Java handle floating point rounding, or how they handle out-of-vocabulary categorical strings, creates a microscopic shift in the data distribution. The model is receiving data that looks subtly alien compared to what it was trained on, and the predictions degrade.
Which leads us to our third architectural scenario.
Okay.
You're developing a custom TensorFlow model on Google Cloud. You have complex pre-processing steps. The absolute requirement is that you must guarantee, mathematically, that you use the exact same pre-processing routine during model training and serving. How do you eliminate skew?
Right. The materials highlight a specific tool for this.
You use TF Transform. It is a library specifically designed to eradicate training serving skew. Instead of writing pre-processing scripts in pandas, you write your transformations using TF Transform operations. You run this logic inside an Apache Beam pipeline on Dataflow to crunch your massive historical dataset for training.
Okay, so that handles the training side, but how does that actually solve the serving side in Java?
Because of what TF Transform outputs, it doesn't just output the clean data, it exports the exact mathematical operations you defined as a static TensorFlow graph. It creates an artifact. When you finalize your model, you physically attach this pre-processing graph to the front of the model. You export them together as a single save model artifact.
Oh, wow.
So when you deploy that model into production, the software engineers don't write any pre-processing code in Java. They just pass the raw, dirty JSON string directly to the model endpoint. The model itself applies the exact same embedded transformation graph it learned during training and outputs the prediction. Because the pre-processing is baked into the model architecture, skew is physically impossible.
It's brilliant. You don't hand the kitchen staff a recipe. You build an automated oven that does the chopping and the cooking perfectly every single time.
Exactly.
Okay, let's hit one final scenario from the materials. The rapid deployment requirement. Let's say you are a data analyst. You have a massive table of customer transaction data in BigQuery. You need to build a machine learning model to predict purchase behavior, but you don't know Python, you don't know TensorFlow, and the business needs a baseline model deployed by the end of the day.
This is where BigQuery ML completely changes the paradigm. It democratizes machine learning for SQL analysts. You do not need to extract the data to Vertex AI. You do not need to write complex Python code. You can train a machine learning model using standard SQL syntax right where the data lives.
You literally just write create model my dataset.purchase predictor as select from transactions. But what if the data needs feature engineering? What if we have those categorical product IDs that need one-hot encoding?
You handle it directly inside the SQL query using the transform clause. Within the create model statement, you define a transform block and use built-in ML functions like ML_encoder or ML_min_max_scaler right on the columns.
That's incredibly powerful.
It is. BigQuery handles the distributed compute, applies the transformations, executes the gradient descent, and stores the model as an object inside the database. It is the absolute fastest path from raw tabular data to a predictive baseline, minimizing architectural complexity entirely.
We have covered an immense amount of ground today. We really have built a masterclass out of these materials. To you, the listener, whether you are actively studying to pass the professional machine learning engineer exam, or you are simply trying to understand the invisible infrastructure that powers the predictive systems shaping our world, I hope this was illuminating. We unpacked the deep optimization mathematics of gradient descent and adaptive learning rates. We dissected the strict boundary between the parameters a machine learns and the hyperparameters a human dictates.
We covered a lot of architecture, too.
Yeah, we explored the business reality of tuning precision versus recall. We navigated the Google Cloud storage ecosystem, exploring how systems like Spanner use atomic clocks to defy latency, and how BigQuery uses columnar architecture to accelerate analytics. We translated human reality into multidimensional vectors using the hashing trick and embeddings, and we explored how architects combine these tools to eliminate catastrophic errors like training serving skew.
The goal was really to demystify the magic, recognizing that enterprise AI is a highly structured, logical, and often fragile pipeline of data plumbing is the first step to mastering it. You now understand the mechanisms behind the illusion.
Exactly. But before we sign off, I want to leave you, the listener, with a final thought to carry with you. Something that builds on the fundamental mechanics we've discussed today. We talked extensively about hyperparameters, the learning rate, the architecture, the boundaries the human dictates before the machine is even allowed to start learning. We spent significant time on feature engineering, how the human chooses to translate reality into numerical representations, deciding which metrics matter and which data is entirely ignored. We talked about thresholds and casting nets based on human business
All
decisions.
right.
So, when a machine learning model operates in the real world, approving a loan, screening a resume, predicting a crime hotspot, and it gets something wrong, or it systematically penalizes a specific demographic, is the system malfunctioning? Is the math broken? Or did the machine operate perfectly? Did gradient descent flawlessly optimize for the objective function it was given? Did the model simply, mathematically, and relentlessly execute the implicit worldview encoded by the human who chose the features, set the learning rate, and cast the net?
That's a profound question.
The calculus is impartial. The architect is human. Thank you for taking this deep dive with us. We'll see you next time.